together this very interesting workshop. And to you all for coming, especially right now. It's dark hours of French football because France is losing 1-0, I just learned from South Africa. So maybe if you get bored right now, at least you are not going to see the French defeat, so that's compensation. What I'm going to try to speak about today is somewhat a different class of problems than what has been discussed. It's about classification and the question whether it's possible to try to build generic representation for classification. What are the underlying problem math applications which are behind? And what I'd like to begin with is with this hypothesis of low-dimensional data, which was explored yesterday by a number of talks. If you are in this situation where you have the luck that your signal, which may belong to a very large space, do belong to a low-dimensional manifold, then you are in a relatively good situation, in which case you may try to discover what manifold you are in and try to perform recognition within this manifold. So there are a number of situations in which this is the case. This comes from a publication of Kaufman where you see different images showing mouses with different expressions. So depending upon the expression, of course, the image is changing, but there are not so many free parameters so that it does stay in a low-dimensional manifold. This is a second type of applications where you have digits which are deformed. You want to recognize digit. And as you can imagine, in that kind of situation, the number of degree of freedom is not so large. You can view all these digits as belonging again to a relatively low-dimensional manifold. And then the issues, as we've seen yesterday, is to try to explore this manifold, find the dimensionality, and potentially do the classification within this manifold. So that's one setting on which there are many applications. Now, in many cases, whenever you deal with real images, audio signals, and so on, this hypothesis is not verified. I mean, you can see this is a very simple example where you have three textures. If I ask you, there are two of these three textures which are identical, it's immediate, and it typically takes 1/100 of a second to find out that these two textures are identical and this one is different. Now, these two textures are simple realization of Gaussian white noise. And a Gaussian white noise lives in the full space in dimension n. There is no chance you may reduce this kind of image to a low-dimensional manifold. Now, this kind of image are textured images. They are not rare. Most images are textured, and most audio signals have their own texture. These are images coming from databases where people want to do recognition in image processing. They are textured, they are very complex. They don't belong to low-dimensional manifold. And people in computer vision know that very well. That's why for a number of years they've been trying to understand how can you reduce the dimensionality of your signal while trying to preserve the essential information for being able to discriminate the signals, the patterns that you want to characterize. And one of the key ideas that is behind this research of many researchers in computer vision is to try to take advantage of invariant. When you have an object here, if it's translated, same object, you want to recognize it independently from its position. So you may try to build a representation which is invariant to position. If it rotates, potentially you may still recognize it. If it's scaled, same thing. So invariance is something very important for recognition, and it could help to build a representation which is of lower dimensionality. Now, one of the things that appeared as very important is the fact that high-frequency information is absolutely key for recognition. And of course, the difficulty is that high frequencies are completely unstable if you take them as such with respect to invariants such as translation. So one of the questions that comes out in the research in computer vision is how to build up representation that keep the high frequency information while trying to build invariants. And there are all kinds of ideas that have been explored, like building histograms of wavelet coefficients, so you delocalize the information with the histograms, or neural networks with pooling functions with many layers where you have many parameters which are being learned, and hopefully which learn the invariants that you need in the process, and so on. All kinds of techniques that may look very ad hoc, but which in fact work quite well. And one of the issues is to try to understand what's happening here. Why is that possible to do so? And again, this key question is how to build invariant while keeping the high frequency information, while keeping the most detailed possible representation in order to have enough information for discrimination. Okay, so if you look at the problem from a math point of view, that's how you may view your problem. So you have a class, several classes of signals, and your class of signals are invariant under a certain type of transformation that you'll suppose belong to groups. For example, signal may be called a digit number 2. If you translate this number 2, it stays still a digit number 2, so it's invariant to translation. And so you want to build a representation which is therefore invariant to that kind of transformation. That means, let me call it phi, this transformation. That means that if your signal is deformed, well, the transformation of this deformed signal should be identical to the transformation of the original signal. Now, what is the main difficulty? The main difficulty is that you don't just have simple group of deformations such as translation, rotations, and so on, but the signals, the patterns undergo deformations, which are non-rigid deformation, and you want to be stable with respect to this deformation. So that means typically that the group parameter is going to depend upon the spatial index. For example, if you think of translation, a simple translation which consists in taking f and transform it in f of x minus tau, but now tau is going to depend upon x so that you have a deformation. Okay? And you want your representation to be stable. It's absolutely key if you want to be able to do discriminations or classification, stable with respect to that kind of deformation. So what typically you want to do is once you've transformed your signal, you want to obtain a metric. And here I'm going to dream that my metric will be a simple L2 metric. You want to build a metric such that the distance that is built here depends upon this deformation. What does that mean? That means that if you look at the L2 distance between phi of f and phi of f deformed, that should essentially depend upon the elasticity component, which is the gradient of the deformation. So you want two things. You want first to be invariant with respect to your deformation, but you want much more than that. You want to be stable so that the distance, essentially, whenever you have a deformed signal, depends upon the gradient of the deformation. So this is basically the picture. You go from a very high-dimensional space, and you have a class of signal here, which is over there, and you have a distance, which is a very complex distance, which basically expresses the similarity between two patterns, which is a kind of elasticity similarity. You want to build a mapping, which is invariant, and which is going to map your space into a lower dimensional manifold. And what you hope is that in this transformed space, this complex metric will simply be described by a simple Euclidean metric. Okay? And the question is, can you find such a phi, and how to construct it? What I'm going to do is to explain how you can do that kind of thing, and to understand how to do that kind of thing, we're going to begin with standard tools. So I'm going to take a harmonic analysis point of view and explain why the Fourier transform doesn't work, why the wavelet transform doesn't work to do that kind of thing, and see exactly what is lacking. And what we're going to see is that you can indeed build up such transformation by using an interference strategy that I'm going to describe, which I call here recursive interference, and I will provide the invariance theorem. What is quite remarkable is what you will see is that you get completely new characterization of stationary processes. Stationary processes are basically right now described by their power spectrum. I'm going to show through that kind of transform. You get a different kind of spectrum, which gives a very different characterization of properties of stationary processes. And I'm going to show here all the work that Johan Brunat is doing for his thesis for classification. He here has obtained very beautiful results showing that once you are in this transform domain, simple linear classifiers, as simple as linear approximation, provides state-of-the-art results for classification on very complex problems where you have deformed digit, deformed textures, and things like that. So that will be, and then we'll finish on the generalization of that. I will mostly work on translation invariants, and then I will show how all these tools extend to invariants to any type of groups. Okay, so let me begin with the Fourier transform to try to understand what's happening and why is it a difficult problem. So let's take a function f that I'm going to translate and I'm going to deform so that with a gradient here that I'm supposed to be strictly smaller than 1. Okay, if it's a simple translation, if you want an invariant representation, the first thing you think of is to take the modulus of the Fourier transform. Because, of course, if you have a translated function, the modulus of the Fourier transform doesn't change. So that looks as an ideal solution. Right. So, but what's happening if the translation is not, translation parameter here is not a constant? Then if you look at the L2 distance between the modulus of the Fourier transform of the signal and its deformation, what you will realize is that indeed it depends upon the maximum variation of tau, but you have another term here which depends upon the regularity of the signal. What's happening basically is that high frequencies are unstable relatively to elastic deformations. You can see that in a very simple example. You have a function in blue here, which is the sum of two packets, one of high frequency here and one here. This function is deformed. That means it's not just translation. The blue packets go here. It's translated by tau 1, but the blue one here is translated by tau 2, which is larger than tau 1. If you look at the L2 distance between these two elements, you will have indeed the difference between tau 2 minus tau 1, but it's going to be multiplied by the largest frequency of the signal. So if you have a very high frequency, and it's quite intuitive, if you have a very high frequency signal, the error is going to be very large, although the difference between tau 2 and tau 1 may be small. Okay? So basically, small deformations yields large error whenever you have high frequencies. Okay, so what's the strategy that many of us have been following with the wavelet transform, and what's the idea? If I have to summarize it, basically the strategy is cheating, and I'm going to explain why the wavelet transform is cheating and why the wavelet transform pays for it. So what's the idea of the wavelet transform? We all know you take the signal and you make a convolution with a wavelet that is dilated, or several wavelets which are dilated. And if you want in 1D a complete representation, then you are going to make sure that your frequency axis is fully covered by your dilated wavelets which are here. In 2 dimensions, you may have several wavelets having different orientation selectivity, which are shown over there. You dilate them, and you cover the full frequency plane. I'm going here to use analytical wavelets, which are complex functions. So I just need to cover half of the frequency plane. And if you do that, have that kind of covering, then the total energy of the wavelet is of the same order of magnitude than the energy of the function. And it's, in that case, it's constructive. It's smaller than the norm of the function. Okay, the theorem that you can prove is that if your function is indeed deformed, if you look at the error between the wavelet transform and the wavelet transform of the deformed signal, then it behaves relatively well. The error has 2 terms. The first term is the relative distance, the maximum size of the translation relative to the scale. And the second term is what you would like to have, which is the gradient of the deformation. So where is that coming from? The proof basically relies on a simple thing. What you do is you have the deformation followed by the wavelet transform. You want to look at the error with the wavelet transform. I'm going to commute these 2 operators. So I now have the 2 operators commuted minus the wavelet transform. And now the difference between the 2 operators commuted. So you have the commutator which appears here. Now this is small if the deformation, the translation is small in front of the scale. Why is that so? Suppose you have a signal which is deformed over there. The blue signal becomes red. After the wavelet transform, it's completely regularized. Okay, so now it's become this very regular red signal. And if it's slightly translated, the red and the blue curve looks very much alike. So the difference are going to be relatively small. And they are going to be relatively small as long as it looks like a translation over the support of the wavelet, hence this term. So basically, you are nearly invariant as long as the deformation is small in front of the scale. So what does that imagine immediately suggest? It suggests the coarse to fine strategy. The idea is you first begin at very coarse scale, and at coarse scale you have a very large scale, so you are pretty much immune to the deformation. And then the idea was to zoom in. You first say basically based on coarse scale I know that here there is a room with people, and then I zoom in and I can recognize each of the person. Now why doesn't work? It doesn't work because at coarse scale, you are working with very low frequencies. And with very low frequency, you can make major errors and think that this is not a room, but that this is the face of someone or anything. You can make very big errors. And then when you refine, you will never resolve these very big errors. And people in computer vision realize, in fact, if you want to do recognition, don't work from the low frequencies. The low frequencies are too much affected by illumination issues and so on. You should work from the high frequency, which are much more informative. And that explains why these big errors that you do at coarse scale, in fact, led to algorithms which are not stable and never really were efficient for recognition. So we are basically back to these questions. How can we use the high frequency information and build invariants from high frequencies? Okay. Clearly, you cannot do that with a linear transform. So what I'm going to look at here is at a way to transform these high frequencies into low frequencies. And the simple idea is to use a modulus. If you take the wavelet transform and you compute the square modulus, don't forget here, in my case, it's going to be a complex wavelet transform. So it's the wavelet transform multiplied by its complex conjugate. The Fourier transform of the modulus squared here, since here you have a product, is going to be a convolution of the Fourier transform of the wavelet with itself. Convolution, that means that you have a correlation between the Fourier transform of the wavelet transform translated by a certain parameter omega. Now, what is the Fourier transform of the wavelet transform? A wavelet transform is a convolution. So the Fourier transform of the wavelet transform is going to be simply the product of the Fourier transform of the function multiplied by the Fourier transform of the wavelet. So basically, you have an information which is there. Now, if you take this and you correlate it with itself, you have everything which is going to be translated in the neighborhood of 0. So the convolution of this function with itself is a function which is now supported in the low frequency domain. So that simply shows that if you take the modulus, you take your information and you bring it to the lower frequency. Now let's take a simple example to see what's happening. Suppose, for example, that you have a musical chord. Okay? You have locally a signal which is a sum of several frequencies. All right? So here's the Fourier transform of my signal. I have few Diracs which corresponds locally to different musical frequencies, to the different frequencies. The wavelet transform is going to isolate all the musical notes, all the frequency which are within 1 octave over there. Okay? Now, you take that and you take the modulus of the wavelet transform squared. What are you going to get? You are going to get the energy of each of these terms, which appears here, plus an interference term. The interference term is going to depend upon the cosine of the distance between these frequencies. Whenever you take a modulus square, you get interferences. And so you get an information which doesn't depend upon each of the frequency, but which depends upon the distance between the frequency. Now, think of it when you have a chord, like a C major. Unless you have a perfect pitch, you will never know it's a C major chord. You will not know whether it's a C major, D major, E major, but you will perfectly know what is the octave, and you will know it's a major chord. What does it mean you know it's a major chord? That means you perfectly hear intervals. You've heard that there was a major third, minor third, and a perfect fifth interval. Well, that's exactly the representation we have here. Here we've forgotten about the frequency. We know what's the octave, but we know the difference of frequencies. So the transform is going to work on these interference terms. We're going to look at the Fourier transform, which only depends upon the distances between these frequencies. And again, these in physics are the interference terms that appears in a number of cases. Okay, now I don't want to work with a modulus with a square because, as you will see, I'm going to iterate this transform, and I want to have a contractive mapping. So let's look at the modulus with squared is a signal, is a function, which has one component which is constant, which basically carries the energies, which is over there, plus a second component, epsilon of x, which basically carries the interferences between the different frequencies. If you take the square root, because I want to take the modulus, you are going to get your constant here, and the square root of 1 plus epsilon x, if you expand it, you are going to get 1 plus 1/2 of epsilon x. These are low frequencies, and you are going to get harmonics. These harmonics basically mostly lives still in the low frequencies, but some are going to spill out outside these low frequencies. However, this signal, this function, has its energy which is still essentially located in the low frequency, again, plus a little bit outside. What we are going to do is work out of these low frequencies. Don't forget my goal. My goal is take a function and map it to low frequencies because I want to build invariance. Okay, how am I going here to use this idea? I'm going to build up an interference tree which is going to progressively map the information towards lower, lower, and lower frequencies. So let's begin with a wavelet transform. You take your signal, and you have the wavelet transform from the finest scale over there up to a coarser scale, and at the very coarse scale, you get the lower frequency that I show in blue here. So first step, I compute the modulus, which basically gives me the first order interference terms. Okay? So you compute the modulus. What does it do? It takes this, it makes a demodulation, and you basically now suddenly have an information which is concentrated in low frequencies. That's true here, in an even lower frequency here, 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 and here. Now, on that stage, I want to have even lower frequencies. So what am I going to do? Yes?
So you compute, you compute the modulus. What you show here below, is it the Fourier transform of the modulus?
It's a Fourier transform of the modulus. It's a Fourier transform of the modulus that I'm showing, which went from high frequencies to lower frequencies. Now, this, which is now a function of x, I'm going to compute its wavelet transform. Okay? So I compute its wavelet transform from this one, this one, this one, and this one. What's happening in frequencies? This function, which was concentrated in low frequencies, I compute its wavelet transform. I redecompose it in bands like that. Identically here, here, and here. Okay? And now you get the idea. What I'm going to get here are second-order interference terms. The information here are differences of differences. Okay? It's like doing the difference between a minor third and a major third interval. I'm going to look at the differences between frequency intervals. And now you get against the modulus, which is going to map you back even in lower frequencies. So you get even lower frequencies and so on. You do that, and you repeat that once more. You get fourth order interferences, and you get, at the root of my trees here, very low frequency functions, plus here, and the last one, I'm going to compute again the interferences. So what do you do here? You get a tree, and at the root of the tree, here at each node, I have a function. Okay? These functions have been computed with taking wavelet transform modulus, taking wavelet transform modulus. But the red, for example, if I take a red node over there, it was obtained with a wavelet transform modulus and then a convolution with a low-pass filter. So this node has gone under only one modulus. This in green are nodes that have gone under two modulus, yellow 3 modulus. So you have different order of interferences that appear at the root of the tree. The operator that was built up is a product of operator, wavelet transform modulus, and so on. Okay? Now, if you look at the total bottom of the tree, if you go until the scale 0, if I suppose that my function is supported on 0, 1, and is 1 periodic, what you easily verify is that these functions don't depend upon x anymore. So you have a set of scalar value which only depends upon the index of the node at the total bottom of the tree. Okay, now I showed that with binary tree because I was in 1D. If you are in 2 dimensions, you have several wavelets. The same principle applies. You do your wavelet transform with your many wavelets, different orientations. And then you take the modulus and you repeat. You make a wavelet transform. And then you repeat and so on. And you get the same kind of product of wavelet transform modulus, and so on. Okay, so what are the properties of this transform? The first property, which is quite immediate over there, is that you have a contractive mapping because you had a product of contractive operator. So if I called the norm of the transform signal as being the sum of the energy of all what I have at the bottom of my tree, sum of the norm of all the signal at the bottom of the tree, you verify that the more you decompose, the more contractive you get. So of course the norm is smaller than the norm of the original signal. That's just because I have a product of contractive operator. The second property, which is much more interesting, is the fact that you're building indeed an invariant representation. So in what sense? If now you have a function which has been translated by a parameter tau that might depend upon x, you have the same kind of results than with a wavelet transform. In other words, if you take the deformed signal which is transformed, the error is going to depend upon the relative size of the translation relative to the scale, plus a term that depends upon the gradient of the deformation. But here you have a parameter which is in front, which is the number of scale of the decomposition. So how do you prove that? It's essentially the same idea. You have the error between 2 operators. I'm going to commute these 2 operators, so I'm going to make this operator appear. And this error is easy to deal with because this is the output of these functions are very smooth. So after translation, you can verify that they are bounded by the scale multiplied by the maximum translation. And here you have your commutator, but your operator is a product of contractive operators, so the commutator is bounded by the sum of the commutators, so you control this term and you get that. Now that looks like a wavelet case, but it behaves very differently. Why? Because now I can let the scale go to 0. In the wavelet transform, if I increase the scale, I basically lose everything. I just have the constant. Here I increase the scale. At each stage, I keep the high frequencies. So it's going to converge to a transform that I call here I0. If I let the scale go to the bottom so it doesn't depend upon x anymore, this term completely disappears, and what I have is a completely invariant representation. In other words, if the signal is translated, the transformed signal is going to be identical. If the signal is not just translated, but is translated and deformed, the error is only going to depend upon the gradient of the deformation, multiplied by something that depends upon the maximum frequency, but it's not the frequency, it's a log of the frequency. So it changes very slowly. The other companion result with that is the fact that it works well also at the first order. So behind this result, there is 2 consequences that I'm going to discuss. What this result says is if I look at the error between the transformed signal and the transformed signal that has been deformed, I can extract at the first order the deformation parameter, and the error is going to depend upon the relative size of the deformation, but to the power 2. What is that giving me? This is telling me basically at the first order, if I look at the difference between the deformed signal transformed minus the original signal transformed, this is going to be of the order of the gradient of the deformed signal multiplied by the deformation parameter. And this is going to be of the order of 0. This is it's exactly like, for example, whenever you have some optical flow problem, translation, this would be the kind of equation you would get with the optical flow equation projected over wavelets. You have the same type of equation. The only thing is that this equation now doesn't just apply to the low frequencies, but it applies to all the frequencies of the signal, given that you've calculated the interferences. So if you want to compute the deformation at a position x, you have a system of equation for all the alpha, and you basically resolve this system of equation for all the alpha. I won't go in that type of application. I want to concentrate on the recognition application, classification. Why is that important for classification? It's important because it basically tells you if your signal is deformed, if you look at the interference transform of your deformed signal, the result is going to live in a low-dimensional affine space whose parameters depend upon the deformations. And that's very important because it tells me that in my transform space, things are going to be much simpler. A very complex nonlinear deformation is linearized and is suddenly going to transform me into a linear space. So I'm going to be able to take advantage of that to do classification. Okay, now, one of the problems, of course, is it's not very complicated to build an invariant transform. You take a signal, you transform it into 0, you are invariant. The key thing that you want to make sure is that you preserve discriminability. In other words, the range of your transform has to be sufficiently rich so that you can indeed discriminate signal. So the question that we're asking here is, let's look at the range of the transform. Suppose I begin with a function whose frequency are bounded, so in between minus n pi and n pi. So I'm in a space of dimension n to the power d. I'm going to map this function by my interference transform, my recursive interferences. And I'm going to map, because I have a nonlinear transform, I'm going to map this space on a nonlinear manifold. And the question that I'm asking now is, how big is this nonlinear manifold? Okay? And in one particular case, when the wavelets are indicator function of frequencies, so it's like Shannon wavelets, exact bandpass filters, then you can compute a lower bound of the dimension of this manifold, and you can prove that if initially your space is of dimension n to the power d, the manifold is of dimension larger than n to the power d over 2. What does that mean exactly? That means that you have your operator. Locally, you can invert the operator over balls of this space, which are smaller, which are of dimension n to the power d over 2, and you build these balls with lacunary Fourier series. That tells you basically that this space, or this manifold, is smaller, but not very, very small. So you have a hope to be able to have strong discriminability properties within this manifold. Now, probably for me, the most fascinating aspect of all this is the behavior of stationary processes. So what's happening if you have a stationary process? If you have a stationary process, you make a convolution with a wavelet. It's a convolution. It's going to remain stationary. Okay? But now you have a complex phase, which is going to live between 0 and 2 pi. Now what do? The next stage, what we do is we compute the modulus. So that means that this random phase, we kill it. So suddenly there is a very strong reduction of variance. Okay? Now, this modulus is also a stationary process, and so you can compute the ratio between the two variants. You know the variance of the modulus is smaller than the variance of the original convolution. And what is the ratio? You verify easily that the ratio depends upon the ratio between the first order moment of this convolution divided by the second order moment, in other words, the variance. This exactly expresses the volume reduction. The variance is getting reduced, so you go from a random process which lives in a bigger volume to suddenly a lower volume. And the reduction is this factor. If f is Gaussian, this reduction factor is exactly 1 minus pi over 4. Now, if you repeat that, each time you compute a modulus, each time you are going to reduce the variance. Okay? And in the case of Gaussian process, it rebuilds its Gaussian properties so that if you iterate, you are going to get a variance that decays like 1 minus pi over 4 to the power p, where p is the order of interferences, how many times you've calculated your modulus. The conjecture that is over there says the following thing. If you begin with a process, so that initially lives in your very big space, potentially Gaussian white noise, so it lives on the whole sphere. You transform your process and you can look at the average, the mean signal, which is the expected value of the transform process, okay? The energy of the mean signal is going to be of the order of the energy of the original process. Second of all, if you look at the variance, the ratio of the variance relatively to the variance of the original signal, this is going to tend to 0, like a power of n, and you can have an analytical expression for the beta in the case of Gaussian processes. The analytical expression, there is a hole in the proof. So the proof is not complete. Numerically, it's verified, and there are good reasons why this expression, but there is not yet an exact proof. What does that tell you? It tells you that you begin with a process which lives in a very large volume. Your transform is going to map this process on your manifold, and it's going to map your process in a much smaller ball around its mean value. And your dream, of course, is that if you have two processes like that, which are very hard to discriminate from a single realization because the two processes live in the same domain of the space, they are going to be mapped in two different domains of your manifold. And if you have that, you won't, because then it's trivial to discriminate the process. You can just compute the Euclidean distance of the transformed element. Okay? I'm going to begin to show that with, before being able to show that, I need to have a numerical algorithm. Very briefly, I'm going to explain how you do that numerically. There is basically an n log n algorithm to do that kind of transformation. Well, the wavelet transform, as you know, you have a fast algorithm which consists in doing convolution, subsampling, convolution, subsampling, convolution, subsampling. That's exactly what we're going to do. So we're going to compute the wavelet transform, but subsampled because we are going to live in lower frequencies, take the modulus, repeat the algorithms, and so on. You have an algorithm in n log n. At the root of the tree, as I explained, I have many signals, which at the limit are constant value. And each of these signals have undergone a number of wavelet transform that depend upon their position. For example, a red dot corresponds to one wavelet transform and then an averaging. A green dot corresponds to two wavelet transform averaging. Yellow dot, 3 wavelet transform and averaging. I'm going to reorder the nodes so that I'm first going to put first order interferences. They just depend upon difference of frequency. Second order interference, third order, fourth order interference. This is a first example, Dirac, okay? The Dirac is transformed. The wavelet I'm taking here is a kind of Gabor wavelet. It's a Gaussian modulated by a sine wave. If you make a convolution of a Dirac with this, you get back the wavelet. You take the modulus, you get back the envelope theta of the Gaussian, basically. So the Dirac is going to be transformed into left of my tree, right, to Gaussian, which are transformed again. That's the next stage interferences, four signals that looks like Gaussians, and so on. At each stage of the tree, if you begin with a Dirac, you get a kind of bump. And you can see that there is basically no decay. Think of it. Fourier transform of a Dirac is flat, while here the interference transform of a Dirac is something which is almost flat in the same way. If you look at a signal which is like a musical chord, so this is a localized sum of several sine waves. Okay? This is the transform where I aggregated all the signal. It looks a bit messy. I'm going to reorder the different signal. Here I have the first order signal. First order signal is like the sum of the wavelet coefficients over all their supports. So that's a wavelet type information. Second order information, it's information about distances, differences of frequency. Third order information, fourth, fifth, it looks almost negligible. And now I'm going to look at two processes. Gaussian white noise, Bernoulli process. These are two white noise. If you look at the power spectrum of these two processes, it's completely flat. So from the point of view of the Fourier transform, these two processes cannot be distinguished. You make the transformation up to the bottom of the tree. That's the kind of measure that you get. It's a signal because it's square integrable. And that's what you get at the bottom of the tree obtained from that. You see they are completely different. Okay? They are clearly can be distinguished. You reorder them, and that's what you get from the Gaussian signal. And you can see that the variance is getting smaller, smaller, and smaller. That corresponds to the 1 minus pi over 4 to the power p. It's the decay of the variance term. And in the case of the Bernoulli process, you still have a decay of the variance, but which is somewhat slow. Okay, so let's look now at applications to classification. I'm going to look at two problems. The first problem will be the equivalent of the recognition of digits that we're going to study afterwards. It's in computer vision, these are called deformable template model. It's a case where you have a signal, F1, that is randomly deformed, like a digit that you deform, and plus some noise. Second signal, it's a second pattern, F2, randomly deformed, plus some noise. Okay, so here are two examples of my two classes. Okay? Now, I have two random processes. I'm going to take these realization of F1, F2. I'm going to map them with my operator phi. Okay? I'm going to look at the mean of the transformation of F1 and the mean of the transformation of elements of F2. If phi is a good mapping, it should map it in two different places of your manifold so that it's easy to distinguish it. How can you see that? You just look at the relative distance between the mapping of an element of F1 to the mean mu1 divided by the distance between this to the mean mu2. Okay? If this is small, that means that all the elements of F1 stays in the small ball around mu1. If this is big, that means you are in such a configuration, the two means are close, and you cannot distinguish it. I used here on the left 4 examples for phi. Wavelet transform at a fine scale, large scale, the original signal, identity, and the modulus of the Fourier transform. If you do that, you look at the ratio. The ratio is of the order of 1. That's what you have here. Why? Because you are basically in that configuration. The means are very close. You look at the ratio, you cannot distinguish from the distance to the mean because the mean is basically the same. That's after that transform. That's the curve you get. This is 0.5. That means that the ratio are between, most of them are of the order of 1/10. That means that the distance between a realization of F1 and the mean is 10 times smaller than the distance with mu2. That means you have very strong separation. Up to, with a low probability, 1/2, where the separation is very clear. Now I'm going to take an example which for me is more impressive because more difficult. You take a realization of a stationary process. Now this stationary process is built with a Bernoulli process. That means that the support of this process is a Bernoulli process. Now on the support, you have a Gaussian white noise. Okay? Now what's the difference between this process and this one is that here you have twice more, the support is twice more dense here than here. But you have again two white noise. From the Fourier point of view, these are completely identical. Now I take these two random processes, I do exactly the same thing. I map them and I look at the relative distance and I look at what's happening with the Fourier transform and so on. Same thing, relative distance remains of the order of 1. It's clear. You take two realization of a white noise, you look at their distance in the spatial domain, you get nothing. You get in the Fourier domain, their white noise, the distance is going to remain of the same order. If you look in that case, you see the distance is always, relative distance, always smaller than 1/2, so you get at least a factor 2, and most probable the factor is of the order of 5. That means you've completely separated your processes. So now we're going to look at the work that Joan Brunat did. He did a very beautiful work showing that given this framework, you can have very efficient classification with incredibly simple approaches. the model is the following. What we're going to consider as being a signal class is a realization of a stationary process that was deformed. Okay? So if you have a stationary process, what we showed is that basically the transformation of any realization is going to stay very close to the mean mu. The second thing that we showed is that if you have a signal that is deformed, the deformation belongs to a low-dimensional affine space. So what we're going to say is basically, if you are within such a model, the transformation is going to be well approximated by a constant plus a component that belongs to a low-dimensional space. In other words, it's going to be well approximated by a low-dimensional affine space. So, again, the idea is I'm going to map my relatively complex class to my manifold, and I say on my manifold, I will be able to approximate any element of this class with a low-dimensional affine space. So the strategy proposed by Johan consists in learning basically the space, and to do the learning, you are going to simply use a PCA transformation. Simply use a PCA transformation because what is the... Okay, so you are now in a problem of classification. So you have different classes. If you have 10 digits, you have 10 different classes. You have a number of training signals. Okay, for each of the class, you have a certain number of training signals. What we're going to do is take each of the training signals, transform them, and compute their mean. We're going to take each of the transformed training signal, and we're going to compute their covariance. Okay? Now, what is the affine space that best approximates such signals? We know what it is. It's simply the space that goes through the mean and whose direction are given by, if you are in dimension n, the n first eigenvectors of the covariance corresponding to the largest eigenvalue. It's a simple linear approximation problem. So we just apply this standard result, diagonalize the covariance matrix, extract the n first eigenvectors. Now, the only thing is that we don't know the complexity of the deformation. That means that I don't know in advance what should be the dimension of my space. So I'm going to use a relatively standard model selection approach, which consists in penalizing the approximation error by the dimension of the space. So what's the recognition algorithm? The recognition algorithm takes a signal f and tries to find the best model. What is a model? A model is an affine space. So I try to look at the transformed signal, approximate the transformed signal by its projection in the affine space. I look at the error. You penalize the error by the dimension of the space. And the best model corresponds to the one where you have the smallest approximation error. So, in other words, the minimum error over all k. Okay, so it's really the simplest type of recognition algorithm. You have two parameters here, lambda, and you have the scale j. Why do you have the scale j? Because sometimes you don't want to go totally at the bottom of the tree. You want to preserve some spatial information. Now, these two parameters, you find them with a cross-validation strategy in the learning phase. So you just learn these two parameters. Okay, now I'm going to show results of that. The first thing I'm going to do is to compare the results with an SVM, support vector machine classification over the mnist digit. So support vector machines work with kernels. The best kernels that have been developed for that are polynomial of order 5th, so that's what we use. You have results that depends upon the training size, how many elements you use for the training. It goes until 60,000. SVM at the end gets 1.4% errors. Now, if you look at the kind of results that you get, there are several things. First of all, it learns much, much faster. With 500 elements for training, that means 50 per class, the error drops to 3.4%, whereas here it was 12%. Why? Because we do dimensionality reduction. We reduce the dimensionality, we learn in a much lower dimensional space. If you look with the 60,000 training samples, we still have an error which is twice smaller. And this is a much faster algorithm, very simple. If you look in terms of degree of freedom for support vector machine, the degree of freedoms is basically the number of support vectors. The number of support vectors grow until 2000, whereas in this case you see the number of degree of freedom in our case is the dimension of the affine space that was selected for doing the approximation, and it grows very slowly. It stays until 150. So that means it's faster, but it's a much lower dimensional model. Now, what is the state of the art? The state of the art, the best results are 0.6%. It's obtained with neural networks, with a multi-layer neural network. Now, what is very interesting is that the kind of algorithm that you have here looks very much like a neural network. What do we do? Filtering modulus over a complex function, filtering modulus, but there is no learning. The learning is totally at the bottom. It's just this simple PCA, but the type of architecture has a very strong flavor. Now, of course, as I said, real images are not so simple. You have texture. So you can introduce one layer of complexification by making a textured digit databases. What did we do here? On the background, you have a white noise of a small variance. On the digit, you have a white noise of a strong variance. You can still perfectly recognize the digit. Now, you send that through an SVM, and it's basically completely lost. Okay? With a standard kernel, the errors are of the order of 60%. In our case, it goes down slower because stationary processes are well mapped to lower dimensional elements. If you look at the number of support vectors, it grows very fast, and there we stopped because it was too long. I mean, it was taking over 24 hours of calculations. Whereas here you can see the number of support vectors is even smaller than in the case where you had a non-textured image.
Why did it go down on the last?
It's a mystery. This case, it goes up and down each time, and we don't have a good. For some reason, yeah. Normally, it should be. We expect that it should increase progressively. Now, somewhere it didn't learn perfectly there, and it increased. But these are experiments that Johan did, and we verified. Of course, I asked him the same question, and so it just shows we are honest. It's not perfect, but yeah, I don't have a good answer for that. Now, the last experiment is texture recognition. Here we took probably the most difficult texture recognition problem that is around in computer vision. So you have the Brodats texture, which are simple flat textures that you have to recognize. Malik, who is from Berkeley, created a databases of texture which are illuminated from all directions. So that one texture under different illumination looks very different. This is one texture, different illumination, different orientation. These one texture under different illuminations. Had huge databases, well, huge, 61 classes. Each class has 92 elements, divided into half, 46 for training, 46 for testing. And he developed a model of 3D texture to do recognition with that, and he got an error of 5.35% to do that. Here, Johan applied exactly the same algorithm. There is not a line that's changed. The same algorithm then for the digits and so on. It's just, you take the image, you transform then with this recursive interference transform, and then you find out the best linear space for doing the approximation. And the result that he gets is somewhat lower error, 4.4%. Now, recently there is a publication by Disserman with Markov random field where he gets 2.57%. But the interesting element is that, and I'm sure each time you can make finer models to improve the result, is that this completely generic transform gets very close to state of the art and is much faster than all these approaches and learns with less elements because, again, you have a very low dimensional model. Okay, generalization to other groups. And I'll go fast, even faster. If you look at that, okay, if I ask you, look at the orientation, try to see what's the orientation. I show you a mask, and I ask you, okay, is this the same orientation or not? Very difficult to say. Very difficult because we have not much precision on orientation measurements. And that's a well-known fact. We have a precision of the order of 10, 15 degrees, so it's pretty poor. Unless you show the two together and it's immediate that they are not parallel. Okay? So when you have the two together, we see very clearly differences of our orientation. It's the same thing then for musical notes. If you hear two musical notes very much spaced, you won't be able to say whether they are the same or not if in between you have a mask. If you are together, you perfectly hear the interval, okay, the interferences. The same principle can be applied here. Imagine that you want to build an invariant with respect to this new group, for example, rotation, but any type of groups. What you're going to do is you take your mother wavelet and you transform it with your group operator, so you get the orbit of the wavelet under the action of the group, and you get a family of wavelets, for example, rotated wavelets. Okay? And now you build your wavelet transform with respect to all these wavelets, which are dilated. I'm going to suppose that the rotated wavelet dilated is the same as the dilated wavelet rotated. In other words, there is a commutation between dilation and my group operator. Now, if you look at the wavelet transform of the signal that was transformed by your group operator, you have the convolution of the deformed signal with the wavelet, which is itself the mother wavelet transformed by your group operator. You put that on the other side, you realize that this is the same thing that the wavelet transform, but not with the same wavelets, the wavelet translated by A, and you have the operator here. Now what that immediately appears is that now you have a problem of invariance by translation, not on X, but on this index. So basically you're going to do exactly the same thing, but on this index. What does that mean? It means that when you do your wavelet transform, you're going to do the wavelet transform with now number of wavelets. For example, these are rotated wavelets, like this. Okay? Next scale, rotated wavelets. Next scale, rotated wavelets. Now you want to build an invariance with respect to rotation, which is in fact very important, partly invariant for vision. That means what you want is now to build an invariant when you move in that direction. That means that now the transform, you're going to do wavelets transform, modulus, wavelet transform, modulus, but along the angle, along the rotation. You're going to do it like that, like that, like that. You're going to get your transform signal. And then you repeat. You go to the next spatial scale. You're going to apply all your wavelets. So you've applied your interference transform along rotation, then wavelet transform in space, modulus, again, invariance in rotation, so on. So it's like, you can view it as, for the one doing neural network, it's like you have many layers, you go from one layer to the next, and then you have a within layer calculation, next layer, within layer calculation, and so on. Same kind of transform. The only thing is that now you have put in the middle the interference operator, but which is a contractive operator. So you still have a product of contractive operator, and basically you get the same kind of theorem. You get the same kind of theorem with the same kind of argument. You calculate the commutator is bounded by the sum of the commutators, and you get the same kind of result. Now, what is important? What is important is that in problems like audio, images, and so on, you don't want to be fully invariant by rotation. We are not invariant by rotation. If you are used to see a face, and suddenly the face is presented to you upside down, you may not recognize it. But we are partly invariant to rotation, and the precision that we have is a relative precision on the orientation. And that's the kind of thing that this type of transform is building. The other, for me, important element is that if you think in terms of learning, the point of view that this is putting together is what you want to learn is the group invariance. If you provide us a group which leaves your class of signal invariant, then you have the architecture of the transform. And the issue of learning then suddenly becomes an issue of learning invariance relatively to potentially esoteric groups. Okay, so what's the conclusion of all this? The first conclusion I must say is that I was very surprised of the property of the transform. I was very surprised because the first thing that was for me quite fascinating was what was happening to stationary processes. The fact that you are mapping suddenly stationary processes to a kind of invariant measure, and that this invariant measure has a very different property than the Fourier transform, is extremely interesting. It's interesting because it gives you a completely different representation of stationary processes. In particular, if you think where the wavelet transform doesn't work well, all fractal, multifractal, what are wideband processes, these are exactly the kind of processes where you have processes which are discriminated by that kind of transform. Other type of problems, there are many mathematical problems that comes from that. What are the dimensionality and the size of this interference manifold? There is a very interesting question from a group point of view, because after all, what did we do? We said, we have a group, and we are building a quotient of our functional space by this group. But we want something more than that, because the easy way to build a quotient is to say, I'm going to take an element of my space, look at the orbit, and make a quotient by the orbit. But here what I want is to have a continuity property respect to the elasticity, to this deformation element. And that's what is key to having stability. What does that mean from a point of view of group theory is kind of question which are very open. There are many applications, and we'll see how far it will go, but at least we're working on these things for image, for audio, for basically for generic classifications, to estimate deformations. Because as I said, whenever you have a deformation, it's linearized. It's linearized with a set of equations, so we should be able to calculate displacement movements in a relatively efficient way. I believe there are very interesting things to understand neural network, and I didn't speak so much about it, but there are all these deep learning algorithms by Hinton, Lequin, Poggio and his team. A number of people are putting together these neural networks. I do believe that it's possible now to begin to do mathematics and understand what's happening. And this is clearly not something very objective, but personally I think there is a chance that this is a good model for biology, because the ear at least has very similar properties. There is a very fascinating thing in audio is the space of timbre, which is completely nonlinear, which really depends upon interferences between frequencies, and it's possible that that kind of thing could explain what's happening. And it's always simple to do, to say it's biologically possible, but let's say at least there is an avenue of research to be done here. At least we'll try. So that's the story. Thanks very much.
Any questions or comments? Rob?
I was wondering, when you set things up initially, you had this iterated 4 times, so you sort of got intermods up to 4 tones.
Yeah.
Was that just for exposition, or is that really where you draw the line? Why?
No, 4 was just because space of my slide. But you begin, in fact, if your function belongs to an infinite dimensional space, you do it all over. You do the wavelet transform and you repeat. If it's discretized, it goes to log n. You have a log n sample, and you have n samples, you go to log n.
What would happen if there was no modulus, or if you were only using that with the wavelet packet?
What you would get is exactly, you're right. Wavelet packet, basically at the bottom of the tree you get a Fourier transform, something very close to a Fourier transform.
So the point, what the modulus does, if you go to the end, what does it change?
Okay, it's everything. Everything. What it changes is that it takes your high frequencies and it maps it to the low frequency. Because you see, the high frequency is completely unstable to translation. Otherwise, you get a Fourier transform, which is invariant to translation, but which is unstable with respect to any elastic transformation. So the modulus is completely key here. Yeah.
I have a question. So your guideline in all your development was invariance, and especially invariance by translation. So what bothers me, if one comes back to your very first illustration where you say I put you 2 realization of white noise and another texture, and of course I can recognize the 2 are white noise. But if I take the first white noise and I translate it whatever way, but it won't it won't match better the second white noise than the texture. I mean,
Yeah.
because
But that's the thing, is that what do you mean? If you take a white noise, you translate it, it's a new white noise, it doesn't correlate, but you will say it's identical visually.
sure, but so yeah. Okay. So you're not trying somehow to say two objects are close if they are mapped into each other by some.
What I'm saying is that L2 distance, we all agree, is very bad because it's not invariant. You want a representation, so ideally, two realizations of the same stationary process, you will say, are identical. Okay? So that's the constraint that you want here. You want to be mapped to basically the same small ball. And in that case of three textures, I want that my two images which look aside gets mapped to the same place on my manifold or very close, and the other one far away. And that's basically what we obtain here. Yeah.
So in the quote-unquote kernel of your map, so you have invariances, say, with respect to the translation of small deformations, what has is in there? I mean, do you know? Your dimension was dropping, say, in the case of bending the function by square root, it was going to the d over 2.
Yeah.
What is in the kernel of that map besides invariances? Do you think it's only the invariances that you wanted, or you're losing something else?
Well, first of all, it's an upper bound, so I don't know how much I lose, but clearly I lose quite of the order of that, okay, because you can see it on the numerical calculation. The thing is, it's very complicated because if you think of all the deformations, they define a huge Lie groups, okay, and if you want to say, for example, if you were to say, I want to be completely invariant with respect to that, your manifold would be very small. You just say, I want to reasonably degrade with respect to that. So, to answer the question, I don't know if I'm invariant with respect to any other thing. And to even say even more honestly, I don't know most of the thing. I mean, we are very progressively discovering the property of this thing. And it is quite, the property of this manifold looks very fascinating. But
there seems to be no precision parameter in that result, in the sense that, exactly as you said, you would have expected that depending on the, say, an infinity norm of the gradient of the tau or something like that, you might get different dimensions, or it's not.
No, because the transform is independent from that. The transform is independent from that. Yeah.
When you think of these, say, methods that run under the flag of non-local means, that depend on comparing different objects and using their similarity in order to do some denoising, would this kind of transformation give you some good similarity model?
No, it's very different. It's very different. I'm going to tell you why. Because non-local means and all these things, they are about regression, denoising, and so on. You want to reproduce exactly what you have here. You want to reproduce it. So what you want is that this should be identical to that. I compute the L2 distance. Here I'm saying this piece of carpet is identical to this piece of carpet. If I want to denoise it, it's a very bad idea to say it's identical. So it's not identical. That's why I'm saying these type of problems are completely different from regression problem, inverse problems, and so on. I'm not there to restore the pixels. On the contrary, I'm there to reduce the dimensionality, to say that two things which are different point by point are in fact very similar. So in the spirit it is different, and mathematically it's very different because the nature of the transform is different. But in the spirit it's different. We've been all working very, very much about restoring the information, getting very hardly the pixel by pixel. It's the inverse problem here almost.
Yes, but you can ask that in the presence of noise, can you restore the similarity of the underlying pattern?
The answer is yes here. For example, here you have the noise, but don't forget, the noise is what? It's just an additive element. So you have your additive element, which is itself a random stationary process, which is mapped to a very localized element. Now, everything is not additive, so it's complex. But it's stable, it's robust with respect to that in that sense. Yeah?
So I have another question. So this deformation, so you illustrated it on several dimensional sequences. The first time series, which is one dimensional, and then images, which is two. Volume, maybe voxel type is 3D. So I believe then you gave this motivation which involved the gradient nabla tau of this deformation in L infinity.
Yeah.
Now, I believe there is a big difference between 1 and 2 and 3D, because in 2 and 3D, because you said that in this recursive application only the infinitesimal part of the deformation matters. So it's a first order linearization with a gradient. And why is in your estimate the full gradient, and why do you not separate the symmetric and the skew-symmetric part of the gradient in 2 and 3 dimensions?
I'm not dealing with rotation here, which appears in a very strong... in that case, it was spatial. Now, when you go from 1 to 2 to 3D, in terms of translation, it's identical. The maths are...
I agree.
Rotation, I didn't develop it, how it would relate indeed to the skew gradient, because I didn't relate it to the spatial gradient. I must say, it's beginning. I mean, there are many... I would love indeed to do it to rotation, get back to the screw gradient, so it has to be done. I mean...
Because then in general, if you take your 8 and you rotate it slightly, it's the same object. Yeah. So your thing should be invariant under this...
Yeah, it should appear. This operator should appear, but I didn't.
So, but you
no, I didn't develop it. Mike, your hand. Okay.
One more. Okay, just wanted to comment on it, a particular hope, or where does the invertibility of the particular transform come in? Because you seem to be expunging the phase, but if you keep that, and in a way, have you gone and shoved all the compactness now into the modulus, and all the particular instability and expansion has gone into the phase that you sort of left by the side for these.
So there are several things. First of all, at the beginning, I thought about keeping the phase and thinking the phase is like wavelet coefficient, you keep details information. And then I realized, no, the phase is really unstable with respect to what I want. I want to remove it. So then what about the inverse? You can view as the inverse exactly as the issue of representation theorem from the Fourier spectrum. When you reconstruct, when you have the power spectrum, you can redefine a process with an integral against an orthogonal process, okay? And you can reconstruct a process which has the same property. You will not be able to reconstruct the same realization, but you can reconstruct the equivalent process. So the question which immediately comes, would it be possible to have a resynthesis of the phase so that you can guarantee that you get back a process having similar property, exactly like the Fourier-Stieltje integral that gives you a representation of stationary processes? This is a beautiful problem, I don't know. But the inverse problem is an issue, and indeed I would like to get a result on that.
Okay. Let's thank Stephane. Rob is very anxious to leave. 1 minute to thank everybody for coming. If you have anything in terms of your administrative issues, please see out there now, right? Because before you go running off. And we wish you all a good trip back home, those that are flying back, and let's hopefully do this again some other time.
And thanks very much, Ron, to you.